Hi, I'm Gabriella, and my protein is Cras. Cras is a relay molecule that plays an important role in cell signaling and regulation of cell growth. Cras is normally found on the inner side of the plasma membrane where it can interact with signaling molecules. Cras is a membrane-bound GTPase that converts between being bound to GDP and GTP, normally functioning as a molecular switch as part of the RAS MAPK pathway. When Cras is bound to GDP, no signals are relayed to the cell's nucleus. Cras must be bound to GTP to become active and transmit signals. When Cras is mutated, the hydrolysis of GTP to GDP is prevented. This favors the active GTP-bound form of Cras. This continuous activation leads to the continuous transmission of growth-promoting signals, driving uncontrolled cell proliferation and contributing to tumor formation. This is my model of Cras. The overall 3D shape of Cras is globular. It has central beta sheets surrounded by alpha helices. Overall, the structure is compact, and Cras does not have any subunits because it is monomer. To represent the primary structure, I use pom-poms as amino acids. To represent the secondary structure, I use spiraled purple pipe cleaners to represent the alpha helices and straight green pipe cleaners to represent the beta sheets. The entire model represents the tertiary structure, which is the folded 3D arrangement of the protein, and the quaternary structure does not apply to Cras. In regards to the protein structure and mutation, normally glycine is present, which is the smallest amino acid. It has a side chain consisting of a single hydrogen atom, which allows for flexibility and a condensed protein structure. It is classified as nonpolar and hydrophobic, with a neutral side chain that does not carry a charge. This lack of charge means that glycine does not form strong bonds, and its small size allows it to fit into tight spaces within proteins. Cysteine, the mutated amino acid, has a side chain containing a thiol group, making it polar and hydrophilic. It is larger than glycine and can form strong covalent disulfide bonds, which will stabilize the protein structure. These differences in properties from the original glycine can significantly alter the protein structure and function. And then this is represented on my model with the yellow pom-pom. The mutated amino acid is located near the GTP binding site in P-loop, which is shown by the black pom-pom. This impacts the function of the cell because with the Cras stuck in its active state, it will constantly tell the cell to grow and divide, leading to uncontrolled cell proliferation and continuous activation of pathways like RAF. This will impact the function of the organism as this uncontrolled cell growth leads to cancer. Tumors form as cells divide uncontrollably, and the mutation in Cras is strongly linked to non-small cell lung cancer. Of course, there are many limitations to my model, one limitation being that the model is not to scale at all. The pom-poms and the pipe cleaners are about the same size when in reality the amino acids would be much smaller than the alpha helices and beta sheets would be. A second limitation is that the model does not show bonds or interactions within the protein structure. The Cras protein interacts with many other molecules which are not shown in this model. A third limitation is that the model does not move. It would be helpful if the model was able to imitate the active and inactive states and visually demonstrate how the bonding with GTP would change the shape of the protein. Thank you for listening to part 2 of my protein project on Cras.